Hi everyone, I'm Catherine Spann, although I like Katharina much better. I'm going to start going by that. I'm a research scientist at the University of Texas at Arlington with LAK Research Lab. And the work I'm presenting today is in collaboration with James Schaeffer, a graduate research assistant with LAK, and Dr. George Siemens. So I approach the topic of self-regulation through a psychological perspective, and this is where I view self-regulation as a broad construct that encompasses the full range of ways in which human beings adjust their behavior. And so although self-regulation, like we've talked about multiple times today, it's contextual, it is relatively stable across the lifespan, meaning that those with low self-regulation during childhood relative to their peers will grow into adulthood showing lower self-regulation relative to people their age. And it's largely predictive of a number of important outcomes, such as SAT scores. It predicts if you're going to graduate college by the age of 25. It predicts other things like physical health and mental health, and as well as the possibility of criminal convictions. So I view self-regulation through this psychobiological model of self-regulation. And this was put forth by Dr. Clancy Blair. And what this model suggests is it really addresses how the ability to reflect on information and direct behavior through intentional, goal-directed, top-down control through those executive functioning processes, how those processes interact with and depend on these bottom-up physiological responses to stress. So what this model puts forth is that at sort of the very bottom level, this at the genetic level, we see that there are individual differences in genes that code for certain receptors for catecholamines and glucocorticoid activity that has an effect on stress response physiology, including the sympathetic and parasympathetic nervous system, which then goes forth to influence our emotional reactivity and our emotional regulation, which of course influences our ability to pay attention and to have executive control. And then importantly, these top-down processes of executive functioning and attention feed back down towards the regulation of emotion and the regulation of stress response physiology, which then ultimately goes back and modifies our genes. So at this top level of executive functioning and of attention, I'll talk about from the psychological perspective, where researchers generally characterize EF as a specific set of attention regulation skills involved in conscious, goal-directed problem solving. And although this specific the relationship between executive functioning skills and self-regulated learning, as we talk about it here, it really remains to be unexplored, but I view it as really synonymous, and especially with its emphasis on goal setting, self-monitoring, and strategy use. I'll talk about how I'm assessing that differently, but I do view these constructs as highly overlapping. And so with executive functioning, there are these three sort of core skills that are involved, listed. So working memory, inhibitory control, and cognitive flexibility are these sort of agreed upon core skills that are involved in executive functioning. And one way that executive functioning is measured is through a task called the dimensional change card sort task. And I'm going to describe this here because this is the task that we used in this study to measure executive functioning. And basically what we have here is that participants are presented with a set of stimuli where they learn 2 rules. Really, one rule is to match by color, and one rule is to match by shape. So they're presented with shapes in either in 1 or 2 colors, and they're repeatedly told to match on color, match on color, match on color, and then the rule will switch and will say match on shape. So you can see that this sort of task is tapping into all 3 of those core executive functioning skills. So you need the working memory to remember what the rules are of the game. You need inhibitory control to override an impulse to choose one shape or the other. And then the cognitive flexibility to go back and forth between the rules. And so you can see that this performance, it greatly depends on the prefrontal cortex, which is heavily involved in self-regulatory abilities. So then on the other, on more of the bottom-up processes, we have stress response physiology and emotional reactivity. And the way in which these can be measured are through the techniques provided by psychophysiology as well as affective computing, which those 2 terms are largely synonymous. And so psychophysiology involves the use of physiological signals to understand psychological processes. And one goal of psychophysiology is to investigate the physiological processes by which emotion is embodied. So emotions, we know we feel them, but they also manifest within the body itself. And we can place various sensors on the body to get at these psychological processes. 2 common psychophysiological measurements that I've heard today that we'll talk about in this study are heart rate and heart rate variability. So it really rests on the idea of psychophysiology, which the brain and body are intimately connected. And heart rate is different from heart rate variability. So, and they manifest through the 2 different nervous systems of the body. So we have the central nervous system, which is the brain and spinal cord, and then we have our peripheral nervous system, of which the autonomic nervous system is a part of that. And the autonomic nervous system is also divided into the sympathetic and parasympathetic nervous systems. So we have the sympathetic nervous system, which you might be familiar with. That's, getting your body ready for engaging in a task. It's focusing attention. You'll see an elevated heart rate and so on. A signal with the electrodermal measurement, that's sympathetic nervous system. The parasympathetic nervous system is sort of the rest and digest. So the system that sort of brings your body back down and sort of lets you rest. And importantly, those 2 nervous systems work together. So they're antagonistic, and they work together to bring your body into a self-regulated state. So the one nerve that's really important for heart rate variability in particular is this, what's called the vagus nerve, which directly connects your brain to your heart and is controlling your heart rate on a millisecond time scale. And so importantly, these 2 are related really through this, what they call the central autonomic network of the brain. It involves various brain regions that directly control the heart and control behavior. And there is evidence that heart rate variability at rest predicts self-regulatory abilities. This is really what drove my research here. And one thing that I was really interested in was how if heart rate variability is measured during a task, how do these 2 sort of play out? So the current study here is we measured a number of different indicators of self-regulation at a local museum. So we had participants that were museum visitors, 8 years of age and older, and we took multiple measures. We had the executive functioning measure, which I described earlier as the dimensional change card sort task. We also had a measure of a self-reported measure of arousal, which was the self-assessment mannequin. So basically, participants would just look at this and rate how they're feeling their energy levels from low to high, and I'll call this self-reported arousal throughout the presentation. Lastly, we had them wear an Empatica E4 wristband, which was the wristband used, described earlier in the keynote. And so this wristband, it's a clinical grade device that allows us to assess all raw data, and it measures both heart rate as well as heart rate variability through a PPG sensor. The sample here, I had over 200 individuals, 228, about 43% males. A wide age range, so I had a minimum age of 8, a maximum of 69, and I had a relatively diverse sample, about 20% Hispanic or Latino, and then you can see the racial makeup there. So to the results, this is basically just looking at heart rate and heart rate variability. So we had a 3-minute rest period for the participants, so we could measure baseline levels of these physiological measures. And if you look on the left side, this is results from heart rate. So we have, you can see at baseline, that's that lower brown bar. Heart rate was significantly lower than during the executive functioning task. And on the right side, you can see heart rate variability. There was no difference in heart rate variability at rest or during the task. And that increase in heart rate is expected when you're engaged in a cognitive activity. You expect heart rate to increase. This is just to say that age is highly correlated with physiological measures. So both heart rate and heart rate variability decrease as you age. And I did have, like you saw, a wide age range, so I get to really see the full spectrum of how these change over age. So the basic relationships here, first of all, you'll see that the first top left, heart rate and heart rate variability, those two are highly correlated, but in the opposite direction, which is expected because we have those two nervous systems at play. We have the sympathetic and parasympathetic nervous system. So they're highly negatively correlated. That second row of self-reported arousal, you'll see that what I report feeling, how I report my energy levels is positively related to my heart rate, but it's not related to heart rate variability. That third row, we have how these three relate to the executive functioning performance. So you see heart rate was not related. There was just no relationship. And then heart rate variability was positively moderately related to executive functioning. And then the same is true for self-reported arousal. And importantly, this relationship between self-reported arousal and executive functioning was a nonlinear relationship. So you can see here that low and high arousal levels, respectively, were associated with low performance. If you're at that sort of average level of arousal, that middle person, if you're reporting on the self-assessment mannequin, that's associated with the highest performance. For the main results, we did multiple regression analyses. The outcome was executive functioning. You can see here that age and heart rate were included to control for these. Other relationships and heart rate variability emerged as the strongest predictor, accounting for about 5% of the variance in executive functioning skills. Self-reported arousal was also a significant predictor. And then importantly, that last term was an interaction term put into the model because it was really clear to me that age was having an impact on the relationship between heart rate variability and executive functioning. And what this interaction looks like is this. So what this is showing is the relationship between heart rate variability and executive functioning skills. And you'll see there's a moderate relationship overall between heart rate variability and executive functioning. But as you age, as you get older, this relationship attenuates. And it's basically just flipped. So you'll see at age 39, that relationship is no longer significant. In this sample, age 28, it was still significant. So that relationship between heart rate variability and executive functioning. This was not a main goal of this research, but and it really isn't clear what this means, but age was having a significant impact on my results, so I'm reporting this. Summary, so this is really the first study to examine heart rate variability during an executive functioning task. What this study shows is that heart rate and heart rate variability are different. Heart rate variability predicts executive functioning skills, and heart rate does not. Heart rate variability is a stronger predictor of performance than self-reported arousal. Implications of this are that first, heart rate variability is an indicator of self-regulation. I think it complements existing approaches, but it doesn't replace existing methods. So we can consider the cost and sort of the ease of measurement that goes along with measuring. But I do think it provides an important and reliable signal for self-regulation. Wearable technology in general, it can offer us a non-invasive, sort of passive measurement approach rather than having individuals self-report, which are largely subject to the individual bias and so on. We can have this sort of non-invasive passive measurement. Age is an important factor, just to reiterate. One idea is that we could possibly adjust our schedules based on self-regulatory patterns. So if we can map these signals out over time, perhaps we could adjust our schedules to meet us at our sort of prime self-regulatory abilities. Lastly, I'll just say that one really strong implication for me is that heart rate variability, we know that it can be increased. So there are certain activities such as deep reflective practices and meditation that have been shown to greatly increase heart rate variability. So if we can increase heart rate variability, perhaps we can increase self-regulation. Thank you.
And we have some time for questions, so please. Phil?
I want to test my understanding. Heart rate variability would, in a sense, test the sensitivity of the parasympathetic and sympathetic nervous systems to make adjustments to stimuli that are being processed. And so is this relationship between heart rate variability and executive functioning reflecting that sensitivity, or am I misunderstanding HRV?
So heart rate variability is really an indicator of the parasympathetic nervous system. So it can be measured on that millisecond time scale, and the only thing that can have an influence on that time level is the parasympathetic nervous system, which is measured through heart rate variability. So not necessarily sensitivity per se, but it really is a strong indicator of our ability to rest and calm down. So bring our body down to a certain set point of self-regulation, not necessarily the sympathetic and parasympathetic working in tandem. Does that make sense?
Thanks, Phil. I'm glad to know these work. I wasn't brave enough in our session this morning to try them out. So can you go back to your correlation outcome slide? So I'm going to ask no, that's the one, a kind of naive and perhaps practical question. I'm looking at these numbers and I'm so impressed at, well, our keynote this morning about the instrumentation and the level of detail, but a lot of people are not going to be able to do what what Sana's done or what you've done. And here you're seeing that self-reported arousal is less than heart rate variability, but how much less? You're going from 0.84 to 0.73 on the effect size. So realistically, in your opinion, is self-reported arousal, a pretty darn good measure for people who can't instrument a whole lab put slap sensors on everybody, and you know what I'm saying?
Yeah, it's a great question. I will say that heart rate variability and self-reported arousal aren't correlated. So I don't think that they're measuring the same thing. So they're sort of different constructs, really. I don't think that one could be replaced with the other. And like I said, I'm not suggesting that, these physiological signals can replace self-report in general, but I think that they add an additional layer. So it's an important question. I think there needs to be more research to say, are there other proxies that we can use that we maybe don't need these physiological indicators? And that may be the case, but the research has to be done to show that.
I'm just wondering, did the subjects, did they have access to the biological feedback? I mean, were they able to then maybe learn about themselves and kind of a biofeedback way over time and then report that somehow?
Yeah. So in this experiment, no, they didn't. But these devices do have real-time feedback. So it is possible in the future to sort of show the participant or the student their particular levels, and they may adjust over time, but not in this study.
All the way in the back.
Great, thanks very much. That was really interesting. I'm fascinated by the finding that you had where the effect seemed to fade with age. I think it's the next slide after this one. I thought that was really an interesting thing to find, and it's one of the, I can imagine all sorts of reasons why that might be, but I wondered if you had any ideas about what's going on there.
Yeah, so like I said, this was not the main purpose of this study, but it was very clear that age was having an impact. The reading that I've done, I've found one description by Cacioppo, who's a big physiological researcher, and there was a couple statements in one paper that said that suggested that these autonomic nervous system indicators, so for example, heart rate variability, are not as strong in older individuals, that they simply just attenuate with age. That's one explanation. That doesn't fully explain the heart rate variability EF relationship, but I think that might be it. And I did have a very, my age sample went to 69, so I am going at sort of much older ages than are typical in a university setting. So that may be one that our signal, we just don't, as we age, the signals don't emerge as strongly.
Can I ask one question about that though? Because you had the executive functioning test, but was that the same for all participants? So did the 8-year-olds do exactly the same test as the oldest participant?
Yeah, so they did exactly the same test, and it has been tested, both reliable and valid for across all ages. The executive functioning measure, we know that self-regulation increases with age, but those scores, every score that I presented here, the executive functioning measure has been corrected for age. So it's normed to the specific age range, and that's provided through the NIH tools. They norm it.
Thanks. Phil?
First of all, everything attenuates with age. I'm speaking from personal experience. I'm wondering, now that I understand HRV, whether you might speculate about whether, if instead of using a measure of EF that was a composite of its three main components, if you segregated those, and particularly about inhibitory control and relationships.
So is your question, do I think that they would correlate the same way?
Or potentially, for instance, is working memory irrelevant? Is inhibitory control reflective or predictive?
With the signals particularly? I'm sorry, I'm not understanding.
I'm wondering, you used a composite measure of EF that puts together all of these three components. I'm wondering if you might improve your prediction increase the size by disaggregating that?
Perhaps. I'm trying to think of executive functioning tasks that would isolate the three components. But that's certainly something that could be tested in the future.
Well, I mean, there are some various measures that particularly were designed to measure inhibitory control that might segregate that from the other elements.
Right. I think that's an important point. The DCCS is a very broad executive functioning measure that includes all of executive control. I think if I did isolate just inhibitory control, I might have a stronger relationship.
If you ever actually took a computer test, you might be able to take it out because there's response times and actual actions. So you might actually separate the two. But it's under. Last questions. I thought there was one more question over there.
Just briefly, I'm wondering what was the R squared for the regression model? How much of executive function could you actually explain?
The full model, of course, I don't have it here, but I believe it was around 10%. I could get that to you.
Okay. If there are no more questions, thank you.
Thank you.